Well, my name is Peter Dunn from the university's press team, and I'm here to interview Alan Bond, who has just received an Honorary Doctor of Science from the University of Warwick at our degree ceremonies, so congratulations.
Thank you.
And he's got for his work as an engineer, in particular as a rocket scientist, and in very particular as one of the creators of the Hotod and Skylon spaceplane concepts. But I understand this is not just an honorary degree, it's an honorary degree which has a particular resonance for you because you have many links to this area. I understand that your son was born in Walsgrave Hospital as was mine, is now part of the UHCW Trust. And I understand that you were very involved in rocketry societies in Leamington Spa.
Yes.
And that some of the rockets that you worked on were actually built and designed and tested around here. So I want to explore that first. So starting with the rocket societies in Leamington Spa, what age were you then? Or how did you get involved with that?
Well, I'd been building rockets since... I was about 12 when I started with the cardboard and gunpowder stuff, modifying fireworks to begin with, making my own gunpowder, which incidentally is very difficult to make if it's going to be a successful gunpowder. There are easier propellants. But when I was 16, I got enough knowledge and decided to do a professional rocket, metal rocket, called Poltergeist, which is still on my wall unit at home. And the objective was to try to get a 10-mile altitude record. And that's where I first sort of opened my lifelong interaction with the British government, because they didn't want me to launch it. And that made it to the front page of the newspapers through the latter half of 1960. And through that, I met a rocket group in Leamington Spa as well as one in North London. And I'd also formed a rocket group back in Derbyshire. So there was 3 different groups got together. We pooled all our knowledge. Unfortunately, we were very complementary in our knowledge. I think ourselves in Derbyshire probably had the edge on some of the theoretical stuff. But the other groups had got the edge with regard to the manufacture and practical side of it. So over a period of 3 years, it was a really, really valuable training ground, both in why chemistry doesn't behave like it says in the textbooks and why engineering doesn't behave like your calculations. But ultimately, we were pretty successful. At least 30% of our stuff flew. And on one occasion, we managed to reach an altitude of about 2 miles. So it was a really good training time.
So where in Leamington Spa was I? Can you remember where you were based?
There were a number of people in Leamington Spa that were the nucleus of that. But most of our meetings took place up in Derbyshire. Of course, we've got a lot of open space up there for flying rockets.
Yeah, easier than Leamington, I suppose.
Yeah, it's quite built up around here even then. Yeah. So most of our meetings took place there, or sometimes we did expeditions into Wales, but obviously that was for the bigger rockets, the multi-stage stuff. But for about 3 years we tested and flew an awful lot of stuff.
And the government didn't want you tested. Why? Because it didn't like it was sort of interfering with other traffic, or was it didn't like you playing with large amounts of gunpowder, or both?
I guess there's an element of both, but unfortunately when it came down to it, in those days, it's not true anymore. It was illegal under the Explosives Act of 1875, and I mean, to government people then and presumably now, it doesn't matter if there's a law against it. There's a law against it, and I mean, I personally think that we were extremely safe in everything we did. We'd got a lot of people that were professionals, a lot older than me, who could handle chemistry, electronics and so on. So I learned a huge amount about the chemistry of rocket propellants from those days. And as I said, the straightforward engineering, doing the stress calculations and understanding why the stress calculations don't necessarily always work. So,
and you got to almost 2 miles, and you came second, I think, in a competition for an altitude record. Is that right? Or in Derby in 1963? Is that, no?
No. I think what you're thinking of there is that. The Daily Mirror ran a contest, which was some suggestions of, I can't remember what it was now, but it was a space competition. And I was one of the finalists in that. I didn't get the prize, But what did happen is that it came to the attention of Val Cleaver, who was probably this country's most outstanding rocket engineer, that I'd been involved in that. And he was a friend of Ken Gatland, who actually did the adjudication. And so Val Cleaver then arranged for me to go to Spade Adam and have a look at Blue Streak engines on test and so on. And that was very, very useful to me, because in my own mind I was already a professional rocket engineer by then. I wasn't looking at hardware I didn't understand. So to actually get there, I mean, that really cemented my love of rockets for the rest of my life, I think, that visit.
And I'll come back to Val Cleaver and Blue Streak in just a minute, but I can't let this go, because I remember reading the very same books later on. But one of your inspirations, I understand, for rocketry was your love of Dan Dare in a very particular story, I'm told, Operation Saturn, published in 1953.
Absolutely correct. You've done your research. So space has fascinated me all my life. I don't remember a time when space wasn't part of my life. And in 1953, I first sort of met Dan Dare on the pages of Eagle. Up until then, I'd been quite content to read the books my father bought me and learn about the solar system and the stars, the sky, astronomy and so on. But there you go, there was this character who didn't have to sit on the ground and look at the sky. And it was in particular in the second episode, the second page, the second week of that particular episode. The St. Christopher was on the launching ramp waiting to go. St. Christopher was the rescue ship. And all the checkout was going on. And I thought, wow,
this is what you wanted.
That's what I've got to do. You know, never mind this sitting at the bottom of the atmosphere with a telescope. Let's get out there amongst it.
So particularly the St. Christopher, you're not the Anastasia, the other ship, but the St. Christopher.
No, the St. Christopher. Yeah. I mean, obviously it was a V2 sort of tarted up a bit and with windows and crew and so on. But nonetheless, it was a rocket, and it had rocket engines. In Dan Dare, they had rather good rocket engines, better than we've ever managed to produce in reality. But even so, there was a lot of imaginative stuff I came to realise later on. But it was that particular image of St. Christopher and then taking off and going to intercept the Nautilus, which had been damaged in space.
Yes.
And this was a completely different world which doesn't yet exist, and it's got to. It's so exciting.
I agree. There's a great artist, Frank Hampson, as well.
Yes.
And you mentioned V2. I wasn't going to mention this, but as you mentioned V2, you had an earlier encounter with a V rocket, a V1, I understand. Is that right?
Yeah, you have done your own work. Well, I mean, I don't remember it. I was only 6 months old at the time, and it was the night before my christening. And a V1, which had been launched presumably from a Heinkel out near Scarborough, was on its way to Birmingham. And right at the back of my folks' house was the local factory, which actually, of all things, produced horsehair for stuffing settees. And it had a very tall chimney. Right. And the V1 narrowly missed this chimney. Yeah. I learned from my brother, who was much older than me, later on in life, that it had actually fallen between Burton-on-Trent and Derby in the end. But I've never managed to track it down. My brother had a newspaper report. My brother's unfortunately dead now, and I was rather hoping it would be amongst his effects, but it isn't. So
you'd have liked to have tracked down that original V1, your earliest rocketry encounter.
Well, my family, of course, knowing my interests, always claim that that's what influenced me, but I doubt I'd be taking much notice at 6 months old.
I doubt it. But you mentioned Val Cleaver and Blue Streak earlier. Yep. That's where we got to. So again, another one of the big names of British rocketry. And Blue Streak, of course, tell us about that. What was Blue Streak?
So what I was planning to do when I left grammar school was go off to Imperial College to do applied maths, because my interest had reverted back to astrophysics. But I was looking for propulsion systems within the context of general relativity even then. And I had some ideas as to how to do it, but unfortunately, for reasons which we don't need to go into, I more rather cocked up my entry into university. Okay. And so having met Val Cleaver and established something of a friendship, I basically sent a Mayday message to him. And so he influenced me to join the Rolls-Royce apprentice scheme. And as soon as I'd got my sort of first years of training out of the way, I applied to get to the rocket department. And the rocket department in those days was working on Blue Streak. So Blue Streak was born in the mid-1950s as the British rocket carrying our nuclear deterrent. But by 1960 it was realised it was very vulnerable. That the Americans had offered us Skybolt. that was a
yes,
failure,
we all
of course.
remember that, yes.
But ultimately, what we finished up with was Polaris.
Yes.
And there's little doubt that as a weapons system, the Polaris was a far more effective weapons system. And so, what to do with Blue Streak? So. The British government offered it to the Europeans to put some upper stages on it and turn it into a European launcher, because it was a very powerful rocket for its day. So on slightly better than Thor, not quite as good as Atlas. So it became the basis of the Eldo launcher. I joined that project. I mean, the program was already going, but I had obviously a lot of knowledge. I didn't need training when I got into that job, and found that I could immediately sort of help out straight away. So I was a contributor to the rocket department right from day one, essentially. But they were also doing an oxygen-hydrogen engine research project on the side. Now, Blue Streak was the bread and butter, so they'd test engines, and then my role was to go into a lot of detail in the performance analysis of the engines, looking for anomalies, seeing whether they'd been checked out correctly, and so on. We had a performance office at Spade Adam as well. They did the sort of day-to-day donkey work. My role was to sort of dig a bit deeper to make sure that there was nothing there waiting to bite us. But the exciting thing was the oxygen-hydrogen engine, the RZ-20.
And we will come to that, because that's crucial, I think, to your development as a rocketeer. But before we leave Blue Streak, which also became Black Arrow, didn't it? And Black Knight
Arrow Black Arrow and Black Knight were separate projects. So Blue Streak was to carry a nuclear weapon. Black Knight was the test vehicle for testing re-entry vehicles that would have supported the Blue Streak nuclear capability. But Black Arrow, it had been recognised for a long time that the technology that was going into Black Knight could produce a small satellite launcher. So Black Arrow was a little bit heavier than the V2, not very much, but could put 250 kilograms into a low Earth orbit, whereas V2 could just about get across the channel with a ton of Amatol into London. So Black Arrow was a really successful rocket, and the great thing is it made use of the engines that had been developed for the Black Knight. But it wasn't a project that I was directly associated with. I did some heat transfer work on the engines, because as they were pushing up the performance, they were starting to run into heat transfer issues in the engines. And I've always hated heat transfer. I loathed it, but it turned out I was always rather good at it. Yes. And so it's one of those funny little things that bites you in life, that something you're good at, even though you don't like it, finishes up dominating everything that you do.
Indeed.
Rocket engines are heat transfer, and so if you want to make good rocket engines, I'm afraid that's where you've got to become an expert. So, and
before we totally leave Blue Streak and Black Arrow, the programs you worked on, that's the other local connection, and that I didn't notice until you taught me, but they were actually parts that were manufactured in Parkside at Rolls-Royce in Coventry and tested in Anstey in Coventry.
So the Black Arrow engines, the Gamma 8 and the Gamma 2 for the first and second stages, were built and tested just up the road in Anstey. And of course, 4 of those vehicles flew. I was at the launching of the first one, because I was also in charge of the engines on the F8 round of Blue Streak, which was being launched pretty much simultaneously with Black Arrow, with a couple of weeks apart. First Black Arrow, unfortunately, was damaged during the launch. Some debris from the launch site hit it in the propulsion bay, and it had to be cut down at 25,000 feet. But ultimately, R3 went on to put Prospero in orbit, and Prospero is still in orbit and will be for hundreds of years yet. It had to be deliberately turned off because it was becoming a nuisance to other people.
Too successful.
Yes. So, but it leaves Britain in a rather remarkable state of having done all that, having achieved all the technology, having put its own satellite into orbit, and then we decided not to go ahead with it.
Yes.
Now,
So-
I am nagged continuously by members of the British government and European Space Agency. We desperately need a light launcher in this country, and you may be aware of the fact that people are looking to build spaceports in this country now. And Black Arrow would have been absolutely perfect. Its specification was precisely what is needed. And I curse the dummies in government that decided to finish that particular programme.
But all is not lost, because some of the things you mentioned have led to a path which could lead us to some space capability in future. Now, you mentioned you hated heat exchanging, the heat exchange part of rocketry, but it became key to everything you were doing there. As I understand it, the first heat exchange problem was about decreasing the amount of fuel you needed, because you could use the heat to itself to reheat the fuel.
So you're thinking about the Sabre engine
And Sabre, indeed,
now.
yes.
So the Sabre engine is a hybrid engine between an air-breathing engine and a rocket engine. And the thing that links them together is being able to get the propellants through the combustion chamber. So you need to get to quite high pressures, and therefore you've got to cool the air. Once you get above Mach 3, the air becomes very, very hot very rapidly. And by the time you get to Mach 5, you're trying to compress air, which is already at 1,000 degrees centigrade. So the answer is to use the hydrogen fuel to cool it. And because of the background I'd built up in heat transfer and thermodynamics, always loved thermodynamics, especially the second law. It is such an aggravating law. I spent many years trying to find ways to prove it wrong, but as a consequence I became something of an expert in the second law of thermodynamics. But combination of the second law plus the heat transfer knowledge was fundamental to realising the Sabre engines, which of course reaction is now the main business of reaction engines, to exploit that whole family of engines. Sabre engine is not just one engine. Sabre engine is a concept which you can adjust the cycle parameters to trade off engine weight and fuel consumption. If you're going to go to orbit, a slightly high fuel consumption is not necessarily a problem, as long as the engine is reasonably light. Whereas if you're on a long cruise mission on the Earth, you want good fuel consumption, and the engine weight is not necessarily an issue. So it turns out that the Sabre engines are able to offer Mach 5 terrestrial cruise capability, as well as the possibility, when combined with a rocket, of going to Earth orbit and doing it reusably. So it's a very exciting range of engines.
There's a key word, reusable. Is that the first reusable concept you came up with, if I'm right, was the HOTOL, HOTOL?
Yes.
Did that use Sabre, or was that something slightly different or earlier?
It was a similar generation of engine, but the actual cycle that the RB545, as it was in HOTOL, that was a Rolls-Royce designation, was rather different. It's what we call an open cycle engine. So in a closed cycle engine, the propellants ultimately all go through the main combustion system, and so you don't throw anything away unused. Whereas in the RB545, the turbopump assembly was driven by a separate hydrogen flow, which was just exhausted over the side, for no other reason than we were still learning about the thermodynamics of these engines. And indeed we still are. Every year brings new advances in our understanding of these engines. You wouldn't believe that the second law of thermodynamics could throw in such incredible complexity and lead to very, very exciting possibilities. So we're not there yet. I mean, there's still a huge range of things that one can see on the horizon that these engines can do.
And it's interesting that we're now trying to get reusable spacecraft again. There's at least two competing designs out there that are fighting for supremacy. Yet your HOTOL design was a horizontally taking off like an ordinary plane design, which is around many years before that. And now I understand Skylon, which does use the Sabre engine, is something that you had part designed to help design, and that may be taken forward by a company called Reaction Engines. Is that right? Can you tell us about Skylon?
So from the original HOTOL project, John Scott, Richard Varvel and myself saw that the government was yet again going to axe all the work that had happened during the 1980s And so in 1989, the three of us formed a company, Reaction Engines, with the sole objective of trying to preserve everything that we'd done. Now, quite how we were going to fund it was a bit of a mystery and all of that sort of thing. And indeed, when Richard Varvel and myself finally dived in the pool, there was a resounding thud because there was no water in it. So we spent a decade, really, the 1990s, moonlighting to sort of pay to keep Reaction Engines alive. But slowly, other people became interested and were quite excited with what we're doing. So investment started to flow. And investment tends to be a bit of an exponential thing. As soon as somebody shows a bit of courage and puts money into an idea, a few other people will put a bit more in. And as that grows, then bigger investors come on board. So we were very fortunate that starting in the 2000s, we started to bring in sort of significant fractions of £1 million in each investment. Excuse me, and that enabled us to put down test facilities. So with the big pre-cooler, exchanging the heat is one thing and doing it efficiently. However, as we've experienced today, there's a lot of moisture in the air, and of course, if you're going down well below zero, which that particular variant of the engine did, that went down to about minus 140.
Gosh.
All the water comes out as frost in the pre-cooler. Now that frost is really peculiar stuff. If you've seen a really freezing, foggy day where you get that really light, feathery stuff all over the tree branches and so on, that's the sort of stuff that you get in a pre-cooler. You'd think, one puff of wind and it blow it away. That frost can stop a pre-cooler running in 5 seconds, give or take a couple of seconds.
Gosh.
And because the heat transfer rates are fearsome that we're talking about, the sort of main pre-cooler of Hotel and Skylon is running at 400 to 500 megawatts of heat transfer. Just to put that into context, if that was a heat exchanger in a nuclear power station, it weighed 200 tons, whereas in Skylon it weighs about 1.25 tons. So that's how far we've had to push the technology in order to make all that work. Right. So the first investment went into actually solving that particular issue, which I'm pleased to say that around about 2007, 2008 we cracked.
Excellent.
And then went on to build a full pre-cooler, which we put in front of a Viper jet engine as a source of airflow. And in 2012 actually demonstrated to the world that that really did work, that you could handle it. And you could run down to these really low temperatures without the frost blocking the whole thing up. So that was what the breakthrough in 2012 really was. Not only the ability to build these incredible heat exchangers. One of our heat exchangers has got sort of many times the surface area of a football pitch, and yet the whole thing is a sort of compact thing, you can stand and look at. Also got miles and miles of extremely small tubing in it.
So it's all wrapped into a very tight area too.
Yeah, so in a real sort of Skylon, each engine has got about 2,000 kilometres of tubing in it. But it's very tiny. It's a millimetre diameter with terribly, terribly thin walls.
So before we move to your last concept plane or rocket I want to talk about, you also have a number of rockets, spaceships, whatever, that are flying, that have ion engines propelling them. You've had several satellites, is that right? Out there, which
me personally, no, but back in the 1970s, again, when Britain was doing pretty well, a guy named Dave Fern, who was the sort of real father of the ion engines in Britain, he'd been pushing ion engines for a long time, but finally, as with all things in Britain, the government decided it didn't want to play anymore, and it all came to a halt. And then in the 1980s, Tony Martin, a long-term colleague of mine working on fusion and starship studies and all of that sort of stuff, we got together. He's a plasma physicist and I'm an engineer. We were both working at the Cullum Laboratory on fusion work at that time. And so we rescued what iron engines we could find around the country and got them back up and running. In the 1970s, the iron engines were working on mercury, which is a no-no these days. And we converted them to xenon, and Tony ran a very extensive program and showed all that was possible. But we decided what we really needed was a bigger iron engine. So the original iron engine was sort of about a couple of kilowatts. So we stretched that up to about 7 kilowatts. And I managed to, by dint of many little favours I pulled in from colleagues around the authority, managed to build the first big iron engine that we tested for pretty much zero cost. My boss always wondered where I'd managed to find the money, and he could never quite work out how I'd managed to fiddle the books. But anyway, we got a 7 kilowatt iron engine on test, which was very, very successful. Now, again, unfortunately, due to the change in fortunes, that bit of the Atomic Energy Authority got sold off and privatised, and all the iron engine work then went off to, it was DERA in those days, but is now Kinetic. And so Kinetic have inherited a huge amount of work that Dave Fern started, that Tony and myself managed to take to completion. And now they've got a very, very comprehensive iron engine program down there. And those iron engines are flying on spacecraft. So,
but again, that wouldn't have happened if it wasn't for the work of all of you.
I think we played a significant role in rescuing it. So I think one of the things I didn't get from Dan Dare is that most of my life was going to be a firefighting job, just trying to keep the technology that we generated alive and not let it die under the dead hand of politicians.
Yes, Dan Dare fought the aliens, you fought the bureaucrats, as it were. Which takes me to the last part. You mentioned fusion and Column, etc. And one of the sort of biggest and most fantastical projects is Daedalus, which is a spacecraft which used sort of basically nuclear fusion in such a way it could get to 12% of the speed of light and possibly get to Barnard's star in 60 years, Alpha Centauri in 40 or 50 years. That was the thing you took forward with the British Interplanetary Society.
That's right. So during the early 1970s, I was involved in a lot of classified weapons work, and I found that was a bit constraining. So I spoke to Tony Martin. Tony Martin and myself had met during the course of British Interplanetary Society activities, and we pushed it to the British Interplanetary Society. It would be a good idea. We thought that the technology was around to have a go at seeing whether a starship could actually be done. I mean, to some extent it was an intellectual challenge at that time. Could human beings ever actually travel between stars? So these days with Star Trek and all of that sort of thing, everybody thinks all you've got to do is get yourself a warp drive. But I mean,
get them in Tesco's.
The reality is that interstellar travel was difficult then and it is now. But we pulled together a dozen or so people looking at different aspects of it. And we spent 5 years from 73 to 78 looking at this in very real detail. So this wasn't just a few sums on paper and then, all right, a bit of unobtainium and maybe this will work or whatever. We tried to make it as good an engineering study as we possibly could. And so in 78 we published that, and that has become pretty much the standard reference now on interstellar flight. There's a new group who have been studying a follow-on, Icarus, who was Daedalus' son, of course. And that has yet to report. Papers keep coming out of it. But at the moment, I think that Daedalus sort of still stands there. There are a lot of warts on it, as you might expect. The thing that we really got wrong was the growth of computing power. The computers on Daedalus weighed 10 tons, and the data storage was sort of bubble memories and megabytes. And I mean, the incredible steps forward that have been taken in electronics were completely missed by the Daedalus team. And yet some of the Daedalus team were very senior people in EMI at the time. And they were on the forefront. And so the incredible, unbelievable progress that's come along in computing technology is
vastly reduced the weight of the thing, which makes it even easier to...
Well, it would increase the capability, because one of the things that came out of the studies using that particular propulsion system is that there's a sort of minimum weight that you can't get over. Just in order to get the electron beam drivers to initiate the fusion detonations and so on. And therefore, there's no point in flying less than 500 tons. And therefore, it's not a question of how small can I make it. It's a matter of, and even when I told the payload team they got 500 tons, their immediate response is, what am I going to put in 500 tons? Which I thought was rather limited in terms of their perception. Yes. You're going to spend 60 years flying to another star. I would have thought that
There's a lot of stuff you might want to pack,
500 tons of stuff would have made it worthwhile. But even with today's technology, I don't think that we could pull down that payload very significantly. The Icarus people want to take longer and actually decelerate. We decided at the time, based on the Pioneer and Voyager missions, that a flyby would be as good as we could do, because at that time we thought 50, 60 years, that's about somebody's career span. Can a project like this actually last longer than somebody's career span? Well, the reality is it can. We didn't know that then. It was the early days of spaceflight, remember. So we erroneously, in my view, now pitch to say that we'd charge off through, and then in a matter of a few hours we'd be straight through the stellar system that was the target. But we would deploy a lot of probes. We'd deploy 18 nuclear-powered probes, which could select various targets and do a close flyby, but completely impossible to actually decelerate from that speed with the ion engines. But Tony and I rolled our ion engine experience into the design of those probes, and so it's a very, very credible mission. But I think we'd do it differently now.
So just to end, obviously, a stunning career with at the back of many bits of technology which have either come to fruition or could take us much further, in fact even to the stars. What would your advice be to a young person now considering either on leaving university and considering a career in engineering, or for that matter about to join university and consider studying engineering? Is it a degree, a path of study which you think is valuable? And
the first thing, take it seriously. You know, you've been imbued with all this knowledge. A lot of people have spent time knocking it into you, and go away and believe it, and apply it. Be enthusiastic, but have individual thoughts, and don't think somebody else has already thought of it. Because whilst people have thought about a lot of things, provided that you can sit down and think, what if, and then push the knowledge that you've gained into checking to see whether that what if actually works, you should get on with it. And quite often you'll reach the conclusion that your peers have actually got it wrong, and that you really can sort of make progress. Even so, the Sabre Engines are a case in point. Second law of thermodynamics is sort of over 100 years old, 150 near enough. And there's nothing in there in terms of heat transfer that hasn't been known for most of the 20th century. And yet you go along and sort of think, well, what if I just did it this way rather than the way that everybody tells me I've got to do it? And watch that entropy thing. Let's not just let entropy expand without limit. And all of a sudden you find that you're in territory that nobody's explored. What you find is that a lot of people have brushed on the edges of it, but not actually rumbled it. Now, that is, a lot of people say kind things about me, but it's really not an intellectual issue. It's just being bold enough, quite frankly, I think that's the right word, to challenge what people tell you. And if you think that something can be done, go away and work it out.